Cross-validation. Cross-validation in machine learning. AI intermediate level. Introduction. In machine learning, evaluating a model correctly is very important. A model may perform well on training data but fail when applied to new data. This problem occurs when the model overfits the training dataset. To obtain a more reliable evaluation of model performance, machine learning uses a technique called cross-validation. Cross-validation allows the model to be tested on multiple subsets of the dataset, producing a more accurate estimate of its real-world performance. Cross-validation is widely used in applications such as fraud detection systems, recommendation engines, healthcare prediction models, financial risk analysis, customer behavior analytics. Understanding cross-validation helps developers build more reliable and robust machine learning models. What is cross-validation? Cross-validation is a model evaluation technique where the dataset is divided into multiple parts, and the model is trained and tested several times using different data splits. In simple words, cross-validation equals evaluating a model by training and testing it on multiple data splits. Example concept. Dataset means multiple splits means repeated training and testing. This approach provides a more reliable estimate of model performance. Why cross-validation is important? If a model is evaluated using only one train test split, the results may depend heavily on that particular split. Example concept. Single split means unreliable performance estimate. Cross-validation helps produce more reliable evaluation results, reduce overfitting risk, use data more efficiently, improve model selection. By evaluating the model multiple times, cross-validation gives a better estimate of real-world performance. Basic train test split. Before understanding cross-validation, it is helpful to understand the basic train test split. Example concept. Dataset means training set plus testing set. Typical split. 80% training data, 20% testing data. However, this method may not fully represent the dataset distribution. Cross-validation improves this process. K-fold cross-validation. The most common cross-validation technique is K-fold cross-validation. In this method, the dataset is divided into K equal parts. Folds. Example concept. Dataset means split into K folds. Steps involved. Split dataset into K folds. Use K1 folds for training. Use the remaining fold for testing. Repeat this process K times. Each fold is used as the testing set once. Example of 5-fold cross-validation. Example with 5 folds. Fold 1 means test. Fold 2 to 5 means train. Fold 2 means test. Fold 1, 3, 4, 5 means train. This process continues until all folds have been used as the test set. The final model performance is calculated as the average of all evaluations. Leave one out cross-validation. LOOCV. Another cross-validation method is leave one out cross-validation. Example concept. Dataset with n samples means train on n1 means test on 1. Steps. Use one data point as test data. Train the model on the remaining data. Repeat for every data point. This method uses maximum training data but can be computationally expensive. Stratified cross-validation. In classification problems, datasets may have imbalanced class distributions. Stratified cross-validation maintains the same class proportions in each fold. Example concept. Balanced class distribution means stratified folds. This technique improves evaluation reliability for classification models. Cross-validation in hyperparameter tuning. Cross-validation is commonly used during hyperparameter tuning. Example concept. Hyperparameter combination means cross-validation means average performance. Techniques such as grid search, Random search. Often use cross-validation to evaluate different model configurations. Advantages of cross-validation. Cross-validation provides several benefits. Advantages include more reliable model evaluation, efficient use of limited data, reduced risk of overfitting, improved model selection. Example concept. Multiple evaluations means reliable model performance estimate. This makes cross-validation a key tool in machine learning workflows. Limitations of cross-validation. Despite its advantages, cross-validation has some limitations. Limitations include higher computational cost, longer training time, complex implementation for very large datasets. Example concept. Multiple training cycles means increased computation time. However, the benefits often outweigh these costs. Cross-validation workflow. A typical cross-validation workflow looks like this. Dataset. Down-pointing arrow. Split into k-folds. Down-pointing arrow. Train model k times. Down-pointing arrow. Evaluate each fold. Down-pointing arrow. Average results. This provides a stable estimate of model performance. Example Python code. Cross-validation can be implemented using scikit-learn. Import cross-validation tools from sklearn. Model_selection import cross_val_score. Example usage. Scores equals cross_val_score. Model x, y, CV equals 5. Calculate average score. Scores, mean. These tools automate cross-validation evaluation. Real-world applications. Cross-validation is widely used in AI systems. Finance. Evaluating credit risk prediction models. Healthcare. Testing disease diagnosis models. E-commerce. Evaluating recommendation algorithms. Marketing. Testing customer behavior prediction models. Autonomous systems. Evaluating perception models in robotics. Concepts learned from cross-validation. Understanding cross-validation helps learners understand. Checkmark how machine learning models are evaluated reliably. Checkmark how multiple dataset splits improve evaluation accuracy. Checkmark how k-fold cross-validation works. Checkmark how cross-validation supports hyperparameter tuning. Checkmark how overfitting risks are reduced. Cross-validation is an essential technique in machine learning model evaluation and optimization. Simple definition. Cross-validation. A model evaluation technique that trains and tests a machine learning model on multiple dataset splits to obtain reliable performance estimates. Final summary. Cross-validation is a widely used technique for evaluating machine learning models. Instead of relying on a single train test split, cross-validation divides the dataset into multiple folds and evaluates the model multiple times. Techniques such as k-fold cross-validation, leave one out cross-validation, and stratified cross-validation provide reliable estimates of model performance. By using cross-validation, developers can select better models, improve reliability, and reduce the risk of overfitting. Understanding cross-validation is essential for mastering machine learning model evaluation and optimization techniques.